What is thixotropy, and how do non-Newtonian fluids use it? Imagine a substance that acts like a solid when still but turns into a liquid when you stir or squeeze it. Sounds strange, right? Well, that's exactly what thixotropy is all about. It's a property some fluids and gels have where they become less thick when force is applied and then slowly regain their original thickness once the force stops. Think of it like a magic trick with liquids. When you shake a bottle of ketchup, it flows easily, but once you stop, it thickens again and clings to your fries. That's thixotropy in action. Now, these special fluids are called non-Newtonian because their viscosity, or thickness, doesn't stay the same no matter how much force you use. And like water, which flows the same way whether you stir it gently or vigorously, non-Newtonian fluids change their flow behavior based on how much stress you put on them. Thixotropic fluids are a subset of these, and their internal structure is what makes them behave this way. When you apply force, their particles or polymers break apart, making the fluid flow more easily. When the force stops, these particles slowly rebuild their network, returning the fluid to a thicker, more solid-like state. You might have already encountered some everyday examples of thixotropic fluids. Ketchup is a classic one. It stays thick in the bottle but flows smoothly when you shake or squeeze it. Paint is another example. It's thick enough to stay on your brush but flows easily when brushed onto a wall. Toothpaste is also thixotropic. It stays firm in the tube but spreads smoothly when you apply pressure. Even some types of gels and certain drilling muds used in oil extraction are designed to be thixotropic. They become fluid enough to flow when needed but then regain stability afterward. This property is incredibly useful in many fields. In cosmetics, it helps creams stay in place on your skin but spread easily when you apply them. In construction, thixotropic materials help control the flow of cement or mud, preventing unwanted mixing or collapse. The time it takes for these fluids to recover their thickness after being stirred or squeezed is called their recovery time, and it varies depending on the material. This memory of stress is what makes thixotropic fluids so interesting. In cosmic or scientific oddities, scientists study non-Newtonian fluids to understand how complex materials behave under different conditions. Their unique flow properties can even mimic certain natural phenomena in space or on other planets. Bizarre physics and chemistry often reveal that these fluids challenge our ideas of how liquids should behave, showing us a world where the rules are a little more flexible. So, next time you see ketchup pour smoothly or paint spread evenly, remember that it's all thanks to the fascinating property of thixotropy. It's a clever way nature and science have found to make materials perform better in everyday life and beyond.